Hello everyone, good morning. Welcome to the class ECE451 Control Engineering. Today we will have a review for the second midterm exam. Okay, it's a ECE451. This is for the 8th week, Wednesday's class. The review for midterm exam 2. All right. The time of the exam, it will be on Monday of the 9th week, so it should be October 19, right? 19. Okay, October 19. And the class time is 9:30 to 10:45, and then you can have 30 more minutes for the you need to upload the file to the Blackboard, right? So totally there should be 15 minutes. Okay, so 9:30 to 11:15. Similar with the first exam, you already have one, right? So similar thing. You have a link. In that link, you can find the problem at that time at 9:30 on that Monday. It's morning. It's morning. Yeah, I will set up a link in the assignment. Same place with homeworks. And there will be a midterm exam. Then you can have the problem there, and when you're done, you can upload your answer to the Blackboard. The time limit is 11:15. So no, don't be late the next time. All right. And I will also send your email with the problem in case something wrong when you try to download the problem or to view the problem from the Blackboard. Okay, this is the exam time. And then the material, if you will cover. Okay, we can see. I have opened the Blackboard here. You go to the Blackboard. You go to material. Actually, we have everything recorded here, right? So we can also see the coverage, the videos and notes for the first week and second week. Those parts we already covered in the first midterm exam. So now we start from here. Start from week 3 until week 8. Week 8. And now this class is the last class in the week 8. All right. Let me click on it. Okay, week 3. We have sections 3.6, right? So let me can I put it in this way? Okay, now I have both. So I have sections 3.6. Actually, this is the stability, about the stability. The stability of systems. And we have the rules table method. Right? Rules table method. And this is week 3. Week 3, Wednesday. Week 3 we only have one class, right? The Monday is the first midterm exam. Then Wednesday we have these. It covers section 3.6. This is only section of chapter 3 will be covered in the in the second midterm. And then we go to chapter 4. So we have sections 4. Okay, let me write in this way. 1, 2, right? They are all belong to chapter 4. And then we check next one. There is 3. I think almost all of chapter 4. 3, then okay, only 3. Anyway, I put it here. Alright. Then go to chapter 5. The sections 1 and 2. This is week 5. Week 5 Wednesday. It's sections 1, 2, and 3. Okay, so these are for until week 5. Then let's go back. Week 5, then week 6. Let's go to week 6 and 8. 6, 7, 8. It's 6, 7, 8. 6 is 5. 6 also 2 and 3. Okay, so we have some sections we separated in different lectures, right? And then sections 4, 5, 6 of chapter 5. And then now go to chapter 6, right? Chapter 6 in sections 1, 2, and 3. Yeah, I didn't cover all of this section, just 1, 2, 3. Okay, so the coverage of material looks like this. In chapter 3 we have 1 section. Chapter 4 I have 3 sections. 5 I have 6, and 6 I have 3 sections. Chapter 4 we only have 3 sections. Let me see. We have regulation. The stability. Oh, maybe I have section 1 in the. Okay. Let me see the textbook. All right. Let's go to contents. Okay. So chapter 3 we have section 3.6. 3.6 is about the stability. So this is one topic. Yeah. And chapter 4 we have 1, 2, 3. Oh, just 1, 2, 3. Okay, so the 4th section is digital control. We will discuss later. We have a whole chapter for digital control. Alright. And then rule lockers. Rule lockers we cover section 1, 2, 3, 4, 5, 6. Okay, yeah. 1, 2, 3, 4, 5, 6. But in 6 I think I only consider some of it. Yeah, only the plot the negative, how to plot the negative for negative rule lockers, and for 2 parameters, right? I discussed these 2. No, I didn't consider the time delay. And then chapter 6 we have 1, 2, 3 sections. We have both plot, how to plot, and how to apply it in the control. In the control, the main result is how to find the neutral stability point, the marginal point. And then section 3 is an adequate stability criteria. Okay, so we have these 3 sections. Alright, so these are the coverage of the material in the textbook. Alright, then the topic. Actually, you can follow these. Then you know the first one is the stability. stability of system, right? And the second one in chapter 4, we have sensitivity. We have the tracking problem. We have the regulation problem. Okay, so these are the four chapter 4. Right? And 1, 2, 3, 4. Then chapter 5, this is rule lockers. Yeah, roughly speaking, just one topic, right? It's rule lockers, but we have a lot of details in this part. You should know how to give the graph and how to apply it in the control design. And then in the next chapter we have two things. One is a bold plot. One is a Nyquist plot. Right. So totally we have 7 topics, roughly speaking, 7 topics. And for details, let me see. For stability, we have two things. One is the location of poles. One is the root table method. Right. We use these two methods to determine the stability. If you can find the poles, then the location of the poles, if all of the poles they are located in the left half plane, then the system is stable. Otherwise, it is not stable. In unstable case, we also have a special case, that is marginal case or neutral case. If the poles are on the boundary of left or right side in the imaginary axis. Right? So this is for stability. And the root table, you just give the table to calculate, find the coefficients. You start from the equation, then you have the table, then finally you can have the first column. Then you change the sign change on the first column. If there is no sign change, then it is stable, right? Yeah. You need to start from the equations. Start from the characteristic equation to give the table, right? Okay. So this is the stability. And for sensitivity, well, just some formula. You should know how to calculate the derivative. So, yeah, nothing special. Just start from the definition. You know how to calculate. That will be fine, right? Yeah. Third one, the tracking problem. For tracking problem, as well as the regulation problem, I gave you something in the class, and that is not as same as the material in the textbook. So in the class, I gave you the tracking problem and the regulation problem in general. So what is a tracking problem? We have a type for tracking problem, right? The type. What is the type? Type for tracking problem. So that is a number k. When input in the S domain, input is Rs is 1 over S k plus 1. Okay. In S domain we have this. Suppose input in S domain this one. Then you can have ESS, which is the limit t go to infinite. This is r of t minus y of t. You can calculate these in S domain, and you can have a value of these. Then we have the type. So ESS equal to 0. ESS is smaller than the infinite, and the ESS equal to infinite. So we have these three cases. Here will be k smaller than that k. Here is k larger than that k. And here is a k equal to this capital K. This capital K is a type. Type is K. Type K. Alright. So this is in general. And when the system is a feedback system, then you know some information about the plant and the loop gain. Then you can have some special formulas that will be make these calculation more easier. Yeah, those part is coming from textbook, so you need to check the textbook. All right. Yeah, this is I gave in my lecture. But for those parts, when you have problems, if you can use the formulas from the textbook, can make things simple. All right. This is for the tracking. And then for the regulation. It is okay. So this is just for the feedback system. This is just for feedback system. So you have a k, you have a not k, some d of s. Then you have plant g of s. And here's a noise. Before the noise go into the system, before the disturb go into the system, here might be some b of s. Then you have a w of s, and you have a feedback. Yeah, suppose you consider system looks like this, or maybe here you have a h. Maybe here you have a h. Doesn't matter. The idea is, okay, the regulation, you have a type. Type for the regulation give us the level, how well the system can cancel these disturb. Then you check the input, the noise here. The noise has order like a k, and if you can cancel it, make it to be 0, then you have a type. Right? And here I still have r. Then we need a number to measure the ability. That means the steady state error. When you have input here, so when w, okay, it's a t. Here's a t. But in S domain, this is 1 over s to k plus 1. We still use this one. Then check ESS will be r minus y, and the limit t go to infinite. Right, it's this one, but now r is 0. R is 0. Only check the disturb signal. Suppose no input here. So this one will be negative limit t go to infinite y of t. You can also or just check y of t. We want to see the limit of this, whether this can be cancelled to be 0. Right? We check this one for t go to infinite. We just check this one. Suppose r of t is 0. Yeah, both we need suppose r of t is 0. Yeah, no input. Then in this case, the only thing only signal go into the system is this noise. The only signal go into the signal is this noise, this disturb signal. And we want to see this limit will be tend to be 0 or not. And the similar thing, this is also related with this k. For fixed system, for some k, this will go to 0, and some other k, this will go to infinite, and there is a bound, and that bound is the type. That bound is type. Okay, I don't write it here. I state, I talk about it. Is all right? Yeah. Yeah, similar with that. So this is the regulation. Now I can, yeah. Okay, this is the regulation. You also have the type. Okay. This is regulation. Then next will be what? The rule lockers. And the rule lockers. Right. For the rule lockers. Rule lockers, you have three things. The first one, you should know how to draw. How to draw this one. Okay. This one actually you can use a computer, but before you apply this like MATLAB, you need to rewrite the system in terms. You can use the computer, use the MATLAB. So rewrite the system as it's 1 plus k ls something here, doesn't matter. What is the denominator? What is the numerator? Doesn't matter. Or as plus k bs, and run rule lockers L of s or rule lockers b over a. Alright, then you can have the rule lockers. So try to write it in this way. Okay. Okay, here's the overall system. This means the overall system. If you have a feedback system, you cannot just use the plant. You need the whole system. You write the whole system. And of course, for rule lockers problem, you should have a k, which can be changed. A parameter k can be changed. So you put the k here. Right. Yeah. Okay. So how to draw the graph? Then you just run this. If you are familiar enough, you can also give a draft just by your hand. It's also fine. All right. And the B, you need to determine some special values. You just give a graph. You still can have those values, but usually the value obtained from the curve, from the graph, it is just kind of estimate, right? So here you need to know how to calculate to find those special values. So we have several kind of values we can consider like that. We know the rule lockers will start from the cross, right? From the pole. You start from a pole. Then, okay, here, the angle. When departure from a pole of that L of S. In MATLAB, the people use G. Something here in MATLAB. Okay, in our textbook we use L of S. Yeah, because this one can relate it with the loop gain. Okay, or G of S. If we use a MATLAB notation in the MATLAB, that will be g of s. Okay. So you should know, you want to know this angle. You want to know this angle when you depart from pole of L of s, right? And okay, this is one. The second one, when the curve, for example, the ruler curves, you have one cross here, one cross here, and one circle, 1 0 here. Then it will have the graph looks like this. And for example, this is the imaginary axis, this is the real axis. Then what is this point? This is the intersection of lockers with imaginary axis. We want to this. Okay, this is the angle, right? We want to know the departure angle. We want to know the intersection here, and also we want to know this is also kind of intersection. This is breakaway point. Break point. Okay, we want to know this. Do you know how to calculate this one? We have formula, right? For the angle, we have a formula. For this intersection, you need to solve the equation, right? You need to solve the equation. It will be 1 plus this one, 1 plus kg of j omega equal to 0. Try to solve this. Solve, right? And the breakaway point, you have as plus kb as equal to 0, and take derivative according to s equal to 0. You try to solve these two, you can have breakpoint. Breakpoint. Alright. And then last one, like here we have lossy go to infinite. We have rule lockers go to infinite. Then this one you should have an angle, right? The angle. That is the angle of the asymptoter, right? So the direction, obviously angle of asymptoter, asymptoter. All right. So you should know the direction. Like if you only have one branch go to infinite, then the direction should be 180 degree. 180 degree. Go this way. If you have two directions go to infinite, two lockers go to infinite, there will be 90 and negative 90, up and down. Right? Two directions. Right? Yeah. If you have three, then one is 180. Here one is 60. One is another negative 60. You need to divide the whole 360 into three pieces, three equal actually pieces. Then each piece is 120 degree. 120 degree, you start from half of 120 degree, that's 60 degree. So you start from 60 degree here, and then plus 120 you get 180. You have this direction, and then another 120. You go to here, you have another direction, so three directions, right? Yeah, that depends how many asymptoters do you have. Okay, and related with this, you also have the center, right? Center of asymptoters. There will be a summation of all the poles minus summation of all the zeros and divided by the number of asymptoters. Right, this is this one. This is the center. And when you calculate the summation of poles and zeros, you can just use the real part of them, because imaginary part, definitely they will be cancelled each other. So you can only just calculate the real part of poles and the real part of zeros. You do the summation, then subtract them. Then you can have divide by the whole amount of asymptotes. Then you can have that value for the center. Then all the asymptotes will start from that center and follow the direction here. Okay, so this is B. So you should know how to determine those special values. And C is for design. Design use rule lockers. For this one, the most important thing is you try to understand the. I think I lost something. I missed something. Let me see. We have the center, we have direction. Oh, we also have the value of K. Sorry, I forgot that. Yeah, I put it here, alright? Uh, 1 plus K G of S equal to 0. So if S equal to S0 is a point in a rule lockers, then the related K is negative 1 over G of S0. So the K, if you check it like here, this is rule lockers, right? You pick any point, you want to know at this point what is the value of K. Then that K will be just 1 over negative G of S0. S0 is this point. You pick this as S0, then you can have this value. This value will be that K. Alright, so that means you choose parameter equal to this value, choose K equal to this value, then the overall system will have this one as its pole. Okay, then using the when you use the rule lockers to design, the main thing and the key point is you should know the meaning of the pole. Meaning of a pole, right? So here you are choosing poles. You can choose poles along the rule lockers. Every point there will be a pole of the overall system with a certain kind of K. Right? Then what is the meaning of the pole? The pole, you should understand for a pole, we have this. If this is the pole, then the distance from here to here, this original point, this will be omega n, and this value will be negative zeta omega n. Alright, so we have these two important values, and of course you can have what is zeta, right? Zeta will be this one as denominator, this one as numerator. That is zeta. That's zeta, right? So I write these as R and these as some A, right? The pole will be A. Okay, this is B. Like this is B, A plus BJ, and R as square root of A squared plus B squared, right? And then this zeta, this is damping rate, right? Damping rate will be negative A over R. So you pick a pole, you can know what is the damping rate, right? And also you know Wn, it will be A squared plus B squared square root. So you pick a point on the rule lockers, you use that point as a pole of the system. You can also, at the same time, you also have this omega n. And then we know for the design, when you want design system, you should have some requirement like about the setting time, rise time, the maximum overshoot, right? You have some requirement on those kind of things, and all those requirement, finally, you can rewrite the requirement in terms of omega n and zeta. So you want zeta to be what kind of value? Equal to some value, or smaller than something, or larger than something, right? You have a requirement. Finally, you have the requirement just on zeta, and also you can have a requirement on omega n. So when you know these two, that means you have a range of these poles. You want the pole located in certain place. That place can make sure zeta and omega n satisfy your requirement. You will pick poles based on those requirements. This is one side. The other side is you want, of course, you have to pick the pole from the root lockers, right? So you need to make some change on the lockers to make sure you can find those poles. Get it? So the requirement, let me see. Requirement of design gives requirement on zeta and omega n. All right, then pick poles from the root lockers. So that the requirement right. So when you want to design, you have a requirement. Then try to change the requirement to be a requirement on omega and zeta, and then you try to pick poles from the root lockers so that the requirement holds. You have the requirement. Right? Every pole, you know, this is omega, this is you have zeta. Then you pick a pole, you can check, okay, are they satisfied the requirement? Yes, okay, you got it. No, then you need to pick another pole. And if you can't find the necessary, can't find the right pole satisfy the necessary requirement, then you need to try to change the root lockers. Can't find the right pole, you need to change the root lockers. How to change? You need to add some controller. As we did in the homework and problem and the examples, you can use a compensation, the lead compensation, lag compensation. Actually, not just those. You can try more if you want. Yeah, you add some kind of controller. Add a controller to change the root lockers. Lockers, LOCUS, yeah, to change the root lockers. Right, and then you can pick poles again. If you get it, you're done. If you not get it, you can't find the right poles, you change again. Right. So this is design. This is how to work in a design way, just like that. All right. Okay, so this is root lockers. And then root lockers is which one? The number 5. Oh, 6 is the bolt plot. 7 is the Nyquist plot. Okay. 6 and 7. Yeah. 6 is the bolt plot. both products similar with the rule lockers. You still have two topics. The first one, you want to know how to draw the graph, right? And second is how to apply it in your design work. So here's the first one, draw the graph. Draw the graph. In the MATLAB, you just use bold of that g of s. This is a g of s. This overall thing. The bold plot of g of s, that is just bold plot of g of s. You know what I mean? In the rule lockers, you use rule lockers of g. That g is a part of the feedback system, and the lockers is for the whole system. And this one, you bold plot of g, that is just for g. This g, it can be still a part of a feedback system, but the bold plot is just for g itself. Right. Yeah, things like that. For example, you have g of s, and overall, I say this is t of s. Now you can consider the bold plot of g and the bold plot of t. The bold plot of g is just for g. Bold plot of t is for the whole thing. Alright, yeah. So you should know how to give the bold plot. What is the meaning? Meaning is just a frequency response, right? Frequency response. Then second thing is find useful information from the bold plot. We have several things. We can have the resonant peak, the resonant frequency. We can have the bandwidth, right? We can have these numbers, and we can have the gain margin and the phase margin. Okay. So basically, we have these numbers we can find from a bold plot, and of course, we can also have those we call what? This breakpoint. Breakpoint. But this is not required. We can find the breakpoint, the information of the breakpoint from the bold plot. Actually, start from here. You can give the transfer function based on the bold plot. Do you have bold plot? Suppose you do not know the transfer function, then you by check the breakpoint, you can go back to give the transfer function. But that is not required in this course. Okay, I believe it here. These numbers you should know how to find it, right? With MR should be here, right? MR and omega R, and this will be bandwidth. Suppose this is a dB times 3, right? And the phase margin and the gain margin, you need to use both. Like here, you have 180. Then you're coming up. So like this. And then the gain margin. Suppose like here's a 0 dB is here. Then gain margin is here. This is gain margin. Gain margin. And the 0 dB, you have a point here. You're going down. Then this part, this is phase margin. Okay. Yeah. Which direction is positive? Which direction is negative? Check the textbook to find it. All right. Yeah. Okay. So this is the bold plot. So what kind of information can we have? Then for control. For control design, you should know the gain margin we have several things. We can have several things. We can have we can know the tracking type. Yeah, actually, you look at this side. The slope at this point give you a power in the G. Then tracking type of this one. You find this tracking type from both plot of G. And not from the both plot of the overall system, just from G. Then you can have the tracking power. You can have the tracking type. And this tracking type sometimes is useful when you design some control thing, right? Add some controller or something. Yeah. And this is one. And second one is gain margin. Gain margin gave you the mutual point, the marginal point. The A is a tracking type. B is a gain margin. Give us the marginal point. And then you know, the not so accurate, but related with the topic is how to the range K so that T of S is stable. Yeah, it is related with this one. You find the range of K so that the overall system is stable. The gain margin of G of S. You can find the range of K so that the T of S is stable. Right. This is a closed loop. This is an open loop. Okay. This is a second one. Let me see, what else can we say? For the both plot in the control, yeah, just like that. Sometimes this is not so sure. Then you can also check the phase marking. Then that can help. But even you have phase marking, you have gain marking, phase marking. This one is not always can be determined. You can determine, you know, that is a marginal point. This one is definitely you can have it. But when the K go across the marginal point, what will happen? Right, go across that point. The system will change from stable to unstable, or another way is from unstable to stable, right? Two direction, from stable to unstable, or from unstable to stable. Both cases that is marginal point, but you just check the phase marking and the gain marking. Sometimes you can make a decision, sometimes you can't. So, but you still should know that this is a marginal point. All right. But we have a way we can make it very clearly. That is a Nyquist plot. Okay, so Nyquist plot. Okay, so for Nyquist plot, we still have two things. You need to know how to draw the graph. Use computers to just Nyquist. Use MATLAB. Nyquist of that G of S. You can just use this one to draw it. Okay, and you can also, or from a both plot, you can have Nyquist. Plot. So you start this one. When you get this one, then you can find this by hand. Not computer. Here's by computer. This is MATLAB. Right. By MATLAB, you can have the Nyquist plot. You can also use hand, but suppose you have the both plot, then you can have it. Right. So this is how to draw the graph. And then the information we can also have the we can have the phase margin, the gain margin, and phase margin. We still can have these two values. You can have it from the Nyquist plot. The thing like your check, this is 0, this is a -1, and the Nyquist plot, suppose like this, is k for the omega positive. Then you have this point. Suppose the distance here is q. Then the gain margin will be just 1 over q. This point is negative q. Okay, this point is negative q. The length here is q. The 1 over q is the gain margin. And also you try a circle, go across -1. So this is a unit circle, right? It's a circle with radius 1. Then here you have a cross point. Then this cross point, then you have an angle. This angle is just the phase margin. This angle is phase margin. Right? So you can know how to get the gain margin and phase margin from Nyquist plot. And the third one, we can have the probability. Confused. We can have the stability based on the Nyquist plot. We have a formula that is a Nyquist to give that formula. It is let me see. Z equal to n plus p. N is how many times the whole Nyquist plot surround this -1. If surrounded it clockwise, then that n is positive. If surrounded in anti-clockwise, this will be a negative value. Right? And the p will be the p is the number of unstable poles of G. And this one gives us the number of unstable poles of T of S. Alright, and here of course this is a T of S is this one. The whole thing is T of S. Right? It's a feedback system. G is a forward gain. Alright. Yeah. Okay, so this is for Nyquist plot. Okay, that will be all the things we were covered for the second midterm. What else can I state here? Can I talk about the exam? Oh, one more thing. The totally problems. The four problems in the exam. Let me write in the first page. Where is it? Okay. I put it here. All right. Problems 4. Okay, we have 4 problems. What else? Okay, that's all for today. That's all for the review. Then if you have any question, let me see. Suppose this review on Wednesday, and Monday we will have the exam. So okay, so I can set a time in Friday. Put it away. I put it in the back plate. Just here. Okay, here. All right, I stayed here and then right here, Friday. You can think this is an actual office hour. All right, I will be there in the one more office hour from 9:30 to 10:30. Yeah. Okay, just our class time 45. Our class time, not exactly class time. Our class is just for Monday, Wednesday, right? So I use Friday, the same time period. Suppose this time you should be free, right? Monday, Wednesday, Friday, the time schedule should be same for you guys, right? So I use this as an actual one more office hour. So if you have questions, you can just attend that. They'll be in the Zoom meeting. I will set up a Zoom meeting, then you can go to that Zoom meeting if you have problem. All right. Okay, that's all for today's review, and see you next time. Bye bye.